Could you help us understand where we are now in terms of like what's working and how well it's working? Like we're not quite at the ChatGPT moment yet. Like where are we? And I think you brought some videos that you were going to show us to like help everybody visualize what the current state of the art actually looks like.
I think where we are is, I think if you have a task where it's okay for the robot to make a mistake, and it's possible for you to set up a mixed autonomy system where you have a person that takes over when the robot make a mistake and provide corrections. It is possible to get to a level of performance where it starts to make sense to think about scaling robot deployment. And the example that I specifically want to highlight here is this blog post that we did with Weave and Ultra. And it's great that these are also, both YC company. I want to provide a little bit of context here first. The context is that Pi is a primarily research organization. We want to focus on building the best model, but we also want to not be tunnel vision. We want to make sure that the model that we built actually going to be useful and actually perform tasks that people in society cares about. And one of the really good way for us to do so is to partner really closely with companies that want to get robot out there today. And the way that these relationships work is that we treat each other like we're on the same team, very free flow of information. And we design a system that try to get the best possible performance for the tasks that this company care about. So let me talk about Weave first. What you're seeing in this video is a system that we built together, folding really diverse item of laundry in a real laundromat in the mission. You can see, people walking outside. And why this task is difficult is because there's just infinite possibility of observation space. Like, clothings are deformable, and no two item of clothing here are the same. And these are also unseen. These are not like clothing item that are seen in the training data.
Yeah, I love this team. They are some of the most cracked people out of Apple I've ever met.
Gary was the partner for Weave. Maybe
Yeah.
I want to like explain like what Weave is and what their company is.
Yeah, I mean, they're actually shipping their first robots into the home. We sort of talked about it as being able to do household tasks like this, and I think they were very inspired by Physical Intelligence's first demos with laundry folding. So it's actually a total trip to hear about it. A year ago we were talking about them doing it, and then now to see them do it working hand in hand with you is really awesome. I think this is a great example of like, you need the model smarts, you need the data collection, and then the hardware and the sort of system integration all working together is just hard to nail. So
yeah, and to get back to your question about why robotic is hard, it is a really hard system problems. Like you need everything to work well and work well together to get this result. And like Weave is such an incredible team for us to work with to get this result. And it actually didn't even take us that long to get this result. It was roughly, well, we set a goal, and maybe it was like 2 weeks afterwards where we got a model and a system that was good enough at performing this task.
It still like blows my mind to see a robot actually folding laundry, because I remember until ChatGPT, I didn't know if this would exist even in my entire lifetime. Because like folding laundry, I mean, it's always been like the Turing test for robotics, because there's no way to like deterministically program a system the way that you did like pre-AI to do this, because the space is like so infinite. And like we've shown that it's possible for us to do, like basically if everyone can do this, like robots will be able to do everything. It's only a matter of like improving it from here.
There was a funny story where when we first published Pi Zero, people thought of us as the laundry company because the demo was just focused on laundry and actually picking home tasks, especially tasks that has to do with deformable object. It's a very intentional choice on our end. We're not just after the home. We really want to make it broadly applicable, but picking home tasks for us to start with has a few benefits. Like one is relatable. You can see the laundry folding demo and you can kind of like grok how this is going to be useful, and you can get a sense of why it's hard. And the second is that it's really easy to set up to test generalization.
You can talk about Ultra, which is your company, Jared, a demo of it.
Yeah, this is Ultra. The thing that I love about this video is you see, it's bright outside, and you see this is 4x speed, and it's 100 minutes. If I scroll to the end, the sun has set.
Oh, wow.
Uh-huh.
That was one
That's
of the big problems in robotics, where it would be so sensitive to the environment. in lighting and mess up the vision system, the semantics and part of it.
Yeah, and the interesting thing here is that it is possible to get to the level of autonomy that the robot is just performing the task. This is autonomy at scale. Like this is ready to be scaled.
Quan, because this task is less familiar than laundry folding, do you want to explain what the robot is doing here and what Ultra is like doing as a company?
Ultra is a company that want to make it really easy to adapt robot to new tasks. And right now they're focusing on logistics space, which is really important because there's lots of labor shortage in logistics. And the task that we focus on together here is, if you order an item from Amazon, you sometimes get this soft pouch that item gets shipped from. And the task here is you have a tray of these items here, and the robot is supposed to pick one of them at a time and place it inside this pouch. The machine will then close it and then pick up the pouch and put it on the left here to be ready for shipping. Now, this part is hard because there are many different types of objects that can be in this tray. And the opening here is actually very narrow. So you see this interesting example of the robot kind of nudging the item to go into the pouch. And that's really hard. Like that require a very good understanding of the scene and like very precise motion to nudge the object into the pouch. The other thing that's hard about this task is the level of autonomy that's required. Like this is running for an entire day. There is still human intervention, I want to say, in this like full day operation. But the level of intervention is actually quite minimal.
This is not just like some like demo station, right? This is actually recorded in an actual e-commerce warehouse where they're actually shipping real products to real customers. This isn't just like a lab.
This is packaging real customer, order for customer to be shipped out in a real warehouse. So this is real operations.
So I think this is really cool because I think when people think about robots, they tend to think of the consumer use cases like we've, because that's, what we're familiar with in our daily life. What I find really interesting is that there's like a million applications like this Ultra thing that you wouldn't think of as obviously like, oh, who packs the like soft pouch of things that you get from like Amazon? Well, there's some person like who does that. And this is like a job that we can now build a robot to do.
The interesting thing about the approach is that you're converting it from a very difficult engineering problem into a operation problems of how do I identify the use case and how do I collect the right data, which is in some sense more scalable because you can build the system that allow you to collect data for many different tasks. So, it's now a problem of how do I scale data collection rather than, for every new task, how do I design a really difficult engineering system to solve it?
YC Startup School is back. We're hand-selecting the most promising builders in the world and flying them out to San Francisco for July 25th and 26th to discuss the cutting edge of tech. Apply now for a spot. Okay, back to the video.
I think one thing that the audience may not know is that you have a very unique technical insight that in the past, robotics folks would have kind of gasped and be shocked because robots need to run in real time. A lot of times, all of the compute runs on device, but you guys have done something very different. Can you tell us more about that so that this works in real time with large models and really well?
So the context here is that we talk to many companies that would like to deploy robots, and one of the first questions we get is what compute unit should we get on the robot? It's expensive, it's going to increase the BOM cost, and they're worried that it's going to go out in fashion very quickly because the model changes, the model gets bigger. How do I make sure that the hardware that I'm going to commit to today is going to be viable for a couple of years? It's very difficult questions. People are often really surprised when I tell them that almost all of the robot evaluation that we run at Pi today, including the really complicated demo that we have shown making coffee, folding laundry, mobile robots navigating around, the model actually hosted in the cloud. And this is not like a cloud as in a server in the office. It's a real cloud. The model is hosted in a data center somewhere, and within this high frequency control loop that is controlling the robot is actually querying an API endpoint that hosts the model, sending it images and language command and getting back action that then executed directly on the robot. And this is surprising because of precisely the reason that you mentioned, how do you actually make it work? This is why it's really important for Pi to couple system, hardware, and model development and research like very tightly together, because like it allows us to solve for this problem. So for example, one of the insight that we have here is that you can actually bury the inference time within the robot control loop, because if I'm a robot, I have enough action for me to execute for the next 100 milliseconds. Like there's no reason for me to wait until I finish executing that action to ask my model for a different action. I can do it as fast as inference, essentially. And so, maybe when I only have 50 milliseconds of action worth left, I can ask for the next sets of action. And when the current 50 millisecond is over, like I have something that's ready for me to continue with, my next 100 milliseconds. So that's one of the insight. The other kind of algorithmic improvement, we refer to them as real-time chunking. Design inference in such a way that there's going to be a delay in how long it takes to query the model on the cloud, basically. Like the problem here, if I get a little bit more technical, is an action chunk is a sequence of action that I can execute on the robot. So, it's not just one action. And if I have an action chunk that I can execute for 100 milliseconds, and 50 milliseconds in, I want to predict another action chunk, and I'm going to transition to that new action chunk after my current 50 millisecond is over. How do I make sure the two are consistent? Like, how do I make sure that if I'm moving this way, the next action chunk is going to continue to allow me to continue to be smoothly moving this way?
You can pre-compute.
Yeah, you can pre-compute, and like that's one of the algorithmic improvement that we've made to make inference using model hosted in the cloud possible.
I studied computer engineering, so I'm not really an algorithms person, but when it comes to systems like that, like pipelining, like get me all over that. That sounds great. That's so interesting.
I mean, this simplifies, it's a brilliant choice because it simplifies so much of the system for the robots. You don't need all these clunky, I don't know, people have two operating systems at sometimes for robots, embedded RTOS and then the regular one and all these complex giant compute and power. And this is what the initial versions of Waymo used to run, basically a server on the trunk. And you can't afford to do that with general day robotics, which is brilliant that you figure out how to do it.
Yeah, you don't have to. I mean, you can do things. Some of it, obviously, has to be some compute there, but a lot of the compute can happen elsewhere. And then there must be a video, like this thing that we're looking at in the top left, like how much of that is sort of like video feedback, how much of it is like local processed. I mean,
yeah, is there any compute locally on this robot, or is it just like a dumb like video camera that streams data to the cloud?
For this, I am not 100% sure, but I am inclined to believe that it's just a dumb computer. Like for this specific video, I don't remember, but I'm just 100% confident that we can make this work with a dumb computer on the robot. And the one other interesting thing about our collaboration with Weave and Ultra is, one, I've never seen that robot in person.
Oh, wow.
Two is I have very little idea about how the robot actually works.
Interesting.
And that's a very intentional choice. Like I want to stay away from that as far as possible. I also don't know how they collect data. Like I intentionally don't ask them this question to understand whether it's possible for an organization like Pi to parachute into their existing system and to work really closely with them on the thing that actually matters to get the system to work, and not have to learn about how they've set up their system, because in a way that's like a more scalable recipe.
Yeah, you completely decouple a lot of the hardware control loop choices from the semantics and planning, which just works. Just brilliant.
Yeah, I mean, I'm really surprised.
It works.
And when we started the company, we thought that real deployment is gonna be it's only gonna be in the conversation like 5 years into the life of the company, because the problem is just really hard. And we're 2 years in, and this is the result that we have. And real like deployment and scaling the number of robots is a really serious consideration today. And so the pace of progress has just been very pleasantly much faster than we expected originally.